Once upon a time, I was playing a card game with my family, where as a small minor part of the game, each player discarded one card on their turn. Player 1 kicked things off by discarding a 6. Player 2 chuckled because he also discarded a 6. Player 3, on the other hand, either didn't have a 6 or didn't want to part with it, so he discarded a 5 instead. The pattern was broken. Amid disappointed sighs from the other players, player 4 discarded a 7 and reassured the table the average was once again 6. You might think this sounds silly, especially since the discard pile had absolutely nothing to do with the rest of the gameplay. But I think the statement made by player 4 that the average value in the discard pile was 6 hints at a way to understand averages distinct from how it's been discussed in my schooling. My goal in this video is to explain why what I'll call the classical average formula isn't helpful for player 4's analysis of the average, and provide a different way to think about the average that I believe player 4 was employing. If your experiences are like mine, the average has always been described loosely as a way to find the center of a bunch of elements, and defined as the sum of things divided by the number of things. This makes for a fairly aesthetic formula on its own, and has a lot of cool properties. Elegant as it may be, I don't think this formula is very useful for computing the average value of a discard pile on the fly. Let's try it out. The first two cards discarded were both 6s, so the average after player 2's turn was 6 plus 6 divided by 2, which is 6. Player 3 then added a 5, so the new average was 6 plus 6 plus 5 divided by 3, 17/3. Finally, player 4 added a 7 to the pile, and the average became 6 plus 6 plus 5 plus 7, all divided by 4. That's 24/4 or 6 again. Do you see a pattern? Why is 7 the card I need to add to make an average of 17/3 become 6? The perhaps surprising answer is that it isn't, at least not always. For example, if we double the discard pile to 6, 6, 5, 6, 6, 5, then the average is still 17/3. But adding a 7 only brings the average up to 41/42, not quite 6. And this brings up the key observation that makes the classical average formula hard to use in this mental math situation. If you want to change the average of the discard by a certain amount, then you need to consider how many cards are in the discard pile. This means extra mental work and tedium. No wonder people don't like calculating the average of discard piles. Notably, at no time in my card game did someone actually say the average was 17/3 though. The much simpler statement that was used is that the average was not 6. We can think of this as a first step. Given a discard pile, what's the easiest way to decide if the average is 6 or not? I like to think of this as making a guess. I'm guessing the average of the pile is 6. Am I correct? After we've had a good feel for whether the average is 6 or not, then we'll explore what we need to add to change the average into 6. Say that the average of some pile of n cards is A. That is, A is card 1 plus card 2 all the way up to card n, all divided by n. Let's do some algebra to find a more useful expression equivalent to this. Multiplying both sides of the equation by n yields n times A is equal to card 1 plus card 2 all the way up to card n. And moving everything to the right-hand side gives 0 is equal to the sum of the cards minus n times A. Though the reasoning may not be obvious, we can split up the negative n times a into n copies of negative a being added together. The reason we might think to do this, and the reason it's useful, is that there's also n positive terms, c1 through cn, and we can rearrange these with the negative a's. All in all, I can rewrite this equation to be 0 is equal to c1 minus a plus c2 minus a plus all the way up to cn minus a. Why is this new equation useful? We can replace the exact average with some guess g. If c1 minus g plus c2 minus g plus all the way up to Cn minus g all equals 0, then g is the average. Otherwise, g is not the average. Let's try this out on the same example as before. We'll say our guess is 6 because we want to know when the average of the discard pile is 6. And when the discard pile is only a pair of 6s, we do expect that average to be 6. True to our calculations before, 6 minus 6 plus 6 minus 6 does indeed equal 0. Also, when we add a 5 to the pile, we compute 6 minus 6 plus 6 minus 6 plus 5 minus 6 is equal to -1, which is not 0. Finally, we can verify that once the final 7 was added, 6 minus 6 plus 6 minus 6 plus 5 minus 6 plus 7 minus 6 is equal to 0. So the average was once again 6. You might be thinking that this is still a lot of math. But notice now that the calculations in each step can be reused as cards are added. The first 3 terms in this last expression are exactly the terms that we added together when there were only 3 cards in the discard pile. We know those summed to -1, so this expression really is only -1 plus 7 minus 6 equals 0. That means to keep our is the average 6 test running the entire game, all we need to do is add the new card's value minus 6 to a running total each time a card is added to the discard pile. Further, there's no division or multiplication needed, so the math's a lot easier to do in your head. When we have a fixed guess g, it stays the same the whole game, that we want to be the average, let's call this running total the score of the discard pile. We're playing a game after all. That is, the score is C1 minus G plus C2 minus G plus all the way up to Cn minus G. We can also write this in sigma notation like this. Anytime the score of the discard pile is exactly 0, our guess G is actually the average value of the pile. This might seem under wraps now, but we're not quite done with the full problem we set out to answer. We can now check if the discard does have an average of any fixed guess G, but how do we know what card needs to be discarded next to make the new average be our guess G, just like player 4 did in the original game? This would be a good time to pause while I turn the page and think about it if that's your thing. The score gives us all the information that we need. Let's say it's our turn, and the discard pile has the cards C1 through Cn. We would hope then that there's a card in our hand we'll call D, which we can discard to make the score 0. That is, we want D such that C1 minus G plus C2 minus G plus all the way up to Cn minus G plus D minus G is equal to 0. Notably, the first n terms of this equation are just the score of the current discard pile, S, the value we've already been keeping track of to decide if the discard pile currently has an average of G. We can substitute this to get S plus D minus G is equal to 0. Now solving for D yields that D, the right card to discard to make the new average G, is G minus S. The average we want minus the current score. Again, that's to say any time that a card whose value is our guess minus the current score is discarded, then our guess is the new average value of the discard pile. Hence, for example, when the discard pile had the cards 6, 6, and 5, and we wanted an average of 6, the score was -1, and the card we wanted to discard was 6 minus -1, which was 7, just like player 4 discarded. For a different example, say the discard pile is a more complex 7, 5, 3, 6, 8, 9, 3, 4, 2, and 5. And we want to discard a card to make the average become 5. Then we would first compute the score S to be 7 minus 5, which is 2, plus 5 minus 5, which is 0, plus 3 minus 5, which is negative 2, plus 6 minus 5, which is 1, plus 8 minus 5, which is 3, plus 9 minus 5, which is 4, plus 3 minus 5, which is negative 2, plus 4 minus 5, which is negative 1, plus 2 minus 5, which is negative 3, and finally plus 5 minus 5, which is 0. All those add together to give us 2 as our score. Hopefully, we've been mentally updating this score in our head each time a card is discarded. Then, the card D we need to discard is 5 minus 2, just 3. Again, assuming we've been computing that score as cards are added to the discard, this small last step is the only missing piece on any given turn. As a reminder, if we wanted to verify that the average of this new discard really is 5, then we need to add all the cards together and divide by the number of cards in the discard pile. In this case, that's 7 plus 5 plus 3 plus 6 plus 8 plus 9 plus 3 plus 4 plus 2 plus 5 plus 3, all divided by 11. That's equal to 55/11ths, or 5. Let's step back a few minutes and look at the classical average again. Earlier we said that to compute the exact average, we needed to track the number of cards in the discard pile, and that the more cards are in the discard, the less impact that a new card has on the average. But with scores, we can tell whether the average is a fixed guess without keeping track of how many cards there are. Did we find a way to compute the average without needing to know the size of the discard pile? Not quite. Without knowing how many cards are in the discard pile, the score can only tell us whether the guess we made is correct or not. To test a different guess, we would need to compute an entirely different score. Knowing the total number of cards does have its use with the score method I've presented here, though. It turns out that if our guess is G, and we compute that a pile of n cards has a score of S, then the exact value of the average is G plus S over n. Besides just using this as an exact way to find the average, this can be used heuristically to decide how close our guess is. If the absolute value of the score is small compared to n, then our guess was pretty good. If the absolute value of the score is much larger than n, many times larger, then our average is further off. This presents the trade-off between the classical average formula and our score method. If we know the average of a pile, but not how many cards are in it, then we can't determine what card needs to be added to make the new average a certain quantity. Alternatively, if we know the score of a pile with a certain guess, but not the number of cards in the pile, we can exactly determine which card to add to make the guess correct, but can't say anything definitive about how close to the guess the current average actually is. If we let our guess be 0, we get that the average is S over n, or C1 minus 0 plus C2 minus 0 plus all the way up to Cn minus 0, all over n. And that's really just the sum of the cards divided by n, which is the classical average formula. With that in mind, I'd say that the scoring method is actually a generalization of the classical average formula. And that about sums it up. The score method is a way you can easily test if your guess of the average is good or not that doesn't involve any division or multiplication, or remembering how many cards are in the discard pile. The better your guess of the average is, the smaller the numbers you need to add together are. It certainly does not antiquate or replace the classical average formula, but I hope it makes for an above-average party trick.